I'd like to welcome you. I'm Karen O'Donohue. I'm with the education team here at the IETF. And so I've got two purposes here. The first one is to introduce our topic and speaker today, and the second one is to solicit your input and comments on tutorials that you would find useful in the future, and even better, volunteers to provide those tutorials. We're working to improve our education program, and we're really looking for feedback on that. And so we'd really appreciate that. So without any, and the other thing is, I'm not positive that the current version of the slides that are uploaded has the tutorial, the survey link in it. But there will be a version uploaded later today that will have the survey link in it. And so you can look at the slides and then click on the survey link and provide brief survey feedback. Alternatively, you could also email to the Edu team, and that'll do it as well. So without any further ado, we have today Justin Risher, who's going to talk about OAuth 2.0. I think he has definitely a long history in this space, and I'm not sure that he really needs much introduction. He also has a long history in the IETF, and we deeply appreciate his efforts. Thank you.
All right, thanks, Karen. All right, I'm a little bit taller than Karen, so here we go. Hi, everybody, and good afternoon. My name is Justin Risher. I'm an independent consultant working out of Boston. You are looking at the entire company of Bespoke Engineering. So hello, everybody. I've done a lot of work with OAuth over the last bunch of years here. And this is, you know, for IETF 101, this is kind of an OAuth 101 class. There's a math joke in there somewhere. But anyway, I have done this course a bunch of different times. This is a distilled version of a 2-day class that I often come in and give to companies. So I'll basically sit down with an engineering team for a couple of days. There's a lot of hands-on exercises and stuff like that. We obviously don't have that much time to get into a super ton of depth here in the next hour, because like I said, it's a 2-day, like a full 2-day class. But there's a lot that we can cover that'll hopefully give you guys a good grounding, you know, in and around OAuth itself and kind of, you know, what it is and how it works and all that kind of stuff. And if you are interested in going really in depth, some guy wrote a book about this. Antonio Sanso and myself published this with Manning Press last year. The code for all of the exercises is open source, as is the case with all of the exercises for that longer version of today's class that I mentioned. And if you stick around to the end of the class, my publisher has given me a discount code on this, so you can get 39% off. Yeah, it's a weird arbitrary value. So you get 39% off if you go through the publisher. That's for both the ebook and the printed book. So if you're interested in that, come grab me after the class. All right, so what is OAuth 2? I'm assuming that a lot of you guys have probably heard of it. I know it's going to be brand new to some of you guys. Like Brian, I know you're really new to this space, so you know, pay attention. So I want to get a couple of answers of what do you think OAuth 2 is? And if we could at all possibly use the mic, and we're going to try and do this part quick. So who can give me an idea, a quick definition of what OAuth 2 is? Or actually just shout it out and I'll repeat it. Nobody has any idea what OAuth 2 is. It's a great place to start. Yes? A third-party authentication mechanism. All right. Anything else? All right, so a lot of people look at OAuth and they'll say, okay, it's, you know, it's an authentication protocol, or it's an authorization protocol, or it's some security thing that lets me log into Facebook, but I don't really know what it is. I just know that I see it all over the place. And so from the specification, this is what OAuth 2 is. Everybody got that? Well, these are the important parts. You know, as we all know, this is the IETF. We take a lot of words to say something very simple, but do so very specifically. So the real important thing here is that it's something that allows a third-party application to get limited access to some kind of service on behalf of somebody who we call the resource owner. In other words, OAuth is fundamentally not really an authorization or authentication protocol. It is a delegation protocol. OAuth is all about delegating a right of access that lets you allow a piece of software, allow an application to access something on your behalf. So fundamentally, that is the design and goal of OAuth. It's not about authentication. It's not about authorization. It's about delegating a right of security authority. And that fundamental understanding will help you see kind of where OAuth fits in the entire sort of large stack of security protocols out there in kind of the wider world. So these are the different players that we have involved. And I realize the text is kind of small on that slide. Unfortunately, it does get shrink down. But you've got access to the PDFs if you want to see these, and I'll point these out as well. We've got a resource owner, an authorization server, a client, and a protected resource. Now, all of these words mean things in the real world, but they mean something very specific in the OAuth space. So the resource owner is an entity, usually a person, but not always a person. It could be sort of a logical entity, but usually we're going to say it's a person that they have access to some resource over an API. Now, that could be a resource that's about them, and often it is. So this is like my account information, my timeline, my photos, whatever kind of example you want to do. Or it could just be something that I just have access to. You know, say I'm working in HR and I have access to everybody's time card information. That's a resource that I have access to, even though it's not necessarily about me specifically. But importantly, what makes this a resource owner in the OAuth world is not just that they have access to it, but that they can delegate that access. So this is the entity who has the right to say, not only this is something that I do, but this is something that I am going to allow somebody else to do as well. And in general, like I said, they're a person with access to a web browser, and for simplification purposes to start out, we're going to assume that that is always the case. We'll go into the exceptions for that later on. Now, the protected resource is an API. Now, this can be any flavor of API that you want, really. OAuth is written around HTTP, but pretty much beyond that, it's kind of up to you. This can be RESTful, this can be SOAPy, this can be any new kind of thing that hasn't been invented. I guess the kids are doing graph APIs these days. OAuth really doesn't care. As long as it's an HTTP kind of resource, you can throw OAuth at it, and it works pretty well. The important thing is not only does this protect things for the resource owner, but it shares things when the resource owner says to do so. Now, the term that really trips a lot of people up is client, because if you're coming from any type of web programming, you're probably thinking the client is the browser. It's not. And you might also be thinking that the client is the HTTP client, which it kind of is, but it also kind of isn't, because an OAuth HTTP client could actually be, an OAuth client could in fact be, and canonically usually is, an HTTP web server. So in the OAuth world, when we say client, what we really mean is whatever piece of software is calling that API, that protected resource that we were just looking at, the client is whatever application is consuming that API. Now, that doesn't necessarily mean that they're like downloading information. They could be purely pushing information into the API, but they are still the client of the API. And for OAuth purposes, it's whatever piece of software is calling that API, that's what we call the client, all right? So whenever I say client here, that's what I'm referring to, not necessarily web browsers, not necessarily HTTP, transaction clients. We're the client of the API, all right? This is fundamentally the problem that we're trying to solve. Like I said, it's a delegation protocol. I, as a user, want this piece of software to go call an API for me. Now, this is a really old problem. We've seen this a lot over the last 20, 30-something years. We've been trying to solve this for a very long time. There's a lot of different ways we could do that. One of the things that you see a lot, especially in enterprise spaces, is that, okay, I'm the client application, so I'm going to have you log into me, and then I'm going to take whatever you used to log into me, your username and password, and I'm going to go replay those at some API and pretend to be you to go talk to the API. This works really great in enterprise spaces. Obviously, there's kind of a big problem here. Well, there's a couple of big problems. First off, you've got somebody stealing your keys. So you've got an application that's impersonating you going off into the other side. And when that request... Yeah, that's useless. So when that request comes into the protected resource in a case like this, how does that protected resource know the difference between me logging in directly as a user or a piece of software logging in to do something for me? It doesn't. Because the only thing in this model that the protected resource can tell is that somebody showed up with a username and password, and that maps to a particular account. This is fully impersonating me as a user, which means that this client application can do anything that is possible on that API for me, whether I wanted it to or not. There's nothing that I can do as a user, as a resource owner, to limit that access. And say I want to turn off access for that, well, pretty much my only option is to change my password, right? That's the only thing I can do to stop that application. And the thing is, if I'm in an enterprise space and using kind of single passwords and you've got a big Active Directory that everything's going through, well, what's going to happen is the next time I log into that application, it's going to get my new password and it can go call the APIs for me again, even though I didn't ask it to. So we're really stuck with a lot of problems here, but it's functional and it works a lot of space. One of the biggest problems with this, though, is that it doesn't work if that protected resource and that client don't speak to the same account. So say I'm logging into something over in Google and they want to call something over at Yahoo, my password's not necessarily going to be the same across those two services. You can't assume that they will be. So when you can't steal the keys, just ask for them. We see this all the time, don't we? You go to even like LinkedIn today, it says, give me the username and password for your email account, and I promise I'll be really good and only download your contacts and not do all of the other wonderful things that I can do with that username and password. So this really has a lot of the same drawbacks as before, but it does have the benefit of this now works across domain. The biggest drawback to this, though, is that it's training users to give somebody the password to a service even if it's not directly related. And this can be a bit of a problem, you can say, right? So what this means is that now when a user goes to an attacker's website, they say, oh, give me the username and password to your email account, and I promise I'll be really nice and only download your address book. They're going to be like, okay, well, LinkedIn did it and nothing bad happened, and Facebook did it and nothing bad happened. So sure, I'm going to go, type it into here and nothing bad will happen, because we're training users to do exactly the wrong behavior in treating their credentials. All right. So what if instead of using the user's password, you have a key that's good for opening any door that it comes across, no matter who's knocking? And this is a pattern we've had for a very long time. We call this an API key, don't we? So the user shows up and they start using this application and says, I need to go call this API on your behalf. But instead of me stealing your password, I have a super powerful password that's just going to show up, and it doesn't matter which user I'm asking for, I can get their information. Now, again, this is really functional within a single security domain, but again, one of the big problems here is that it can go access my information. This application can go access information without any input from me, without any even action from me. I don't even have to log into this application for it to be able to trigger that. It can just go pull all of my stuff whenever it wants to, whether I did anything here or not. And again, this doesn't really work across security domains. So we use this all the time in enterprise spaces, even today, and a lot of web APIs kind of use this pattern as well. But there's a lot of downsides to it as well. It's also a bit more complicated because now I have to design my API so that you tell me what user you're asking for, and I need to be able to input that, and I have to fully trust you to always, as the client, always do the right thing. So let's combine a couple of different aspects here, and instead of a universal key that's good for everything, let's create a new service-specific credential. Call it a token. And for my account, as the resource owner, I'm going to get a special password made, and I'm going to hand that to the client application so that it can call the protected resource for my behalf. So this is no longer my regular password that I use to log in. This is a special password just for calling this API. And we've seen this all over the place, and this is really starting to get closer to what we want. But this has some drawbacks too. So on the upside, the security model of this is great, because that token, maybe I say this token is only good for read access. Maybe it's only good for an hour. But it's the protected resource now knows the difference between me logging in and this client logging in on my behalf, because it's a different credential. It can map those to different security models. That's really great. The biggest problem here, though, the usability sucks. It's really awful. One of the biggest examples that we had of this in the real world was Google Code. Anybody here remember Google Code? So Google Code, and I'm dating myself a little bit, but there's a lot of gray beards in the room, so I'm okay. And Google Code was a subversion hosting service. They later added Git when that was the cool thing. But in order to access your subversion repository from your subversion client, instead of entering your Google account password, You had to go to a special page, and it was about 3 menu layers deep, and generate a service-specific password for your Subversion access on Google Code, and then copy and paste that into your Subversion client instead of your normal Google password. And again, the security model of this is great because now you have something that is very specifically for Subversion. You can rotate your Google password and this one and this other one independently. Really, really kind of good stuff. This is only good for Subversion. They can't go download your Gmail or anything else like that. Really awesome security profiles. But the problem is developers still screwed this up all the time. Now, these are developers. This is people like us, like the nerds of the nerds, are still screwing up the usability of this because it's too complicated and technical. That should tell you something about how usable this would be for an average user. Because I hate to break it to you, but we're not average users. We need to remember that when we're designing these systems. So we're getting closer here. And really, what I think the answer here is that we take the thing with the good security practices and we automate it. We automate it, we improve the usability, and we sort of make that part better. So we're going to do that with a little protocol called OAuth. And in OAuth, you've got this component called the authorization server. Now, this is added into the mix. We've still got the resource owner, client, and protected resource just like before. But we've now got the authorization server to kind of bridge the gap between all of those and manage this connection. This generates those tokens, those service-specific credentials that I talked about before, like this is a special password for this piece of software to call this API. That's generated and managed by the authorization server. This is also where the user logs in, where they say, yes, this software can go do this thing. And it manages all of those authorizations, which means this can also turn them off or say this is only good for reading and this is good for reading and writing, or whatever other things you need in your API design. All of that is represented, all of those rights are represented in this thing called the OAuth token, specifically the OAuth access token. This is a representation of that triangle of entities. So from the resource owner to the client for the protected resource. All of that gets bundled up into the token. And it's used by the clients, and so it gets issued by the clients, but the format's actually opaque to the clients. So all of these are perfectly valid OAuth tokens. I get a lot of questions from new developers like, what does an OAuth token look like? It's kind of whatever you want. Really. So, I mean, the first one here is just a hex blob. The second one is a type 4 UUID. So that's 112 bits of entropy if you got a good random number generator. The third one, does anybody recognize what that third one is? That is a specific format. Just yell it out. It is base64. You're correct. But beyond that, it is a JWT, a JSON Web Token. We'll get... we might get more into that later if we've got time. So what this is this is a structured format that is base64 URL encoded JSON with a signature applied to it in a sort of semi-detached mechanism. That's the Jose suite of specifications, and that's another tutorial. And the last one here is a high entropy word list choice. So there's 4 random words. I think that's like 160 something bits of entropy, something on that. I forget. The funny thing about this is that these are generally, secrets like this are generally meant to be human memorizable, and an OAuth token really isn't. People never really see the token. So why would you ever use something like that? Because you can. OAuth really doesn't care. OAuth does not care what the token looks like. All right. So, whoops, forgot to check ahead on my slides. Now I have a question. Who here has used OAuth? Just raise your hand. All right. Most of the hands went up. So who here has ever used a Facebook application or logged into a site with Facebook? Who here has ever logged into anything with Google? Who here has ever used Spotify? Yeah, Spotify's applications. Who here has ever used Steam for gaming? Okay, who here has a smartphone? Well, guess what? You've used OAuth. It is literally everywhere. OAuth 2 is everywhere on the web these days. And like a good security protocol, you usually don't see it because most of the time it's just sitting in the background and doing its job. But if you've ever been turning on a new application or connecting a native app to to an account or something like that, and you've seen something like this type of approval screen that says, hey, there's a thing that wants to go do stuff, chances are you're using OAuth. And if you're not using OAuth, you're probably using something that should be running OAuth but thinks they're cleverer than the IETF and probably has some big security holes, which as an independent consultant, if you find one of those, call me, because that's fun work. All right. Now, a brief history of OAuth 2. Now, back in 2006, everybody was using passwords to get to APIs, HTTP basic, right? And if anybody here is from the HTTP auth group, I'm sorry, I'm going to say how bad HTTP basic is, though you probably already know that. So the whole idea behind HTTP basic was that, hey, we've got this great web protocol. We need some way to authenticate it. Let's use usernames and passwords because we use that for everything else. Awesome. Problem here is that allows for, and it really kind of encourages, this kind of impersonation setup like we were talking about before. And so it was really all about the, you give me your password, I promise I'll be nice, and I will go call that API for you. And a couple of internet companies came up with proprietary solutions for delegated access. We had BBAuth, AuthSub, and a handful of others. And also, remember back, 2006 was 12 years ago, but remember what the internet looked like back then. MySpace was the top site. The iPhone wasn't out yet, or it sort of came out, but the App Store wasn't there yet. So imagine a smartphone with no apps. It's really weird to think of that, right? Android was still a couple years off. The internet was a really kind of different place 12 years ago. And so back then, we had a couple of small sites. One was Magnolia, a startup which has since evaporated. The other was this little social messaging platform called Twitter or something like that. I think they're still around. They got together and they're like, hey, we've got a cool thing, you've got a cool thing. We want to plug our cool things together. Problem is that they were both looking at using OpenID for login. Now, OpenID is a federated identity protocol, not the topic of today's conversation, but that means that there is no username and password. So to get to the Magnolia API, there was no username and password that you could present. And by their very design, federated identity protocols don't allow you to replay them. That's a really good security benefit. So neither of them wanted to really build up their own additional proprietary protocols. So they thought, you know what, we're going to get together, we're going to talk to a bunch of interested people, and we're going to create a standard that a bunch of us can use. And that was OAuth 1.0. No formal standards body, just a bunch of smart nerds in a back room at OSCON came up with this document, published it out on the web, and said, hey, here's the thing. And as what usually happens when a bunch of smart nerds get together in a back room, they publish it, and almost immediately a session fixation attack was found baked into the protocol, and the inscrutably named OAuth 1.0a was released right after that. Thing is, though, this actually worked pretty well. And pretty soon, a lot of people started to use it, and people decided, you know what, we're going to kind of get this together, clean up the language a little bit, and it did get published here in the IETF as RFC 5849. So people start using this thing. It solves a problem. It solves a very real problem. Back in 2006, 2008, this time frame, the sort of API economy, RESTful design of APIs, all this other stuff was really starting to come online. Mobile apps were starting to maybe look like they might be a thing. And so this solved a very real problem that people had in a way that was, elegant and fairly usable for most cases. So much so that in something that usually doesn't happen, and as I'm speaking to a standards group, you guys know this, the big players who already had their proprietary solutions said, you know what? We don't want to invest in our proprietary solution anymore. We're just going to use this standard that a bunch of smart nerds came up with instead. So Google and Yahoo and all of these other big players, and eventually, Facebook and all this, alongside Twitter and others, decided, you know what? We are going to use this OAuth standard instead of our own authorization and delegation protocols. And that's actually a really cool thing. And it's something that I think as a community in the IETF, we need to study more how that happened, because that doesn't happen nearly often enough. Usually the open standard gets put on the shelf right next to all of the proprietary standards that everybody else needs to support. So anyway, people start using it, and they start using it for all kinds of off-label fun stuff, like native applications. That started to become a thing. It didn't start out as a thing when OAuth was originally invented. Suddenly, people had like applications on their phones, and Google came up with some really interesting ways to deal with this in the OAuth 1.0 world. Don't have time to get into the details right now. Ping me after if you want the details. People started to use this as delegation when there was no user in the loop, which doesn't make sense because it's a delegation protocol. But people realized that, well, I can delegate rights to non-person users and entities and stuff like that. So I want to use this to be able to replace API keys. That way, my user-facing APIs and my non-user-facing APIs use the same structure. There's a lot of value to that from an architecture perspective. So they started to use OAuth in ways that it was never intended. And OAuth made a lot of assumptions about key placement and stuff. OAuth 1 made a lot of assumptions about key placement. So you ended up with people distributing it in ways that it was never meant to. So that brings us to version 2.0. And like with any second version of the system, it's no longer a protocol. It's now a framework, because that's what we do as nerds, right? But in all honesty, it was chopped up in a very deliberate way. So OAuth 1.0 tried to solve all problems for all use cases all in one go. OAuth 2.0 said, you know what, we're going to look at how people are really using it and focus on those specific problems. And we're going to come up with patterns that reuse all of these components in slightly different ways so that we can actually pull this stuff together. Removed a lot of the pain points, like a proprietary signing mechanism, whatnot, and that got standardized in RFC 6749 and 6750. Already, it's 2 documents instead of 1. You can see it's starting to be modularized more. So what this means is that OAuth 2 is not really a single protocol. You can have 2 implementations of OAuth 2 that don't talk to each other because they're using different parts of the protocol framework. But you get a ton of code reuse. You get a ton of pattern reuse. You get a ton of really powerful stuff from an architecture and engineering standpoint that when you go to solve your one problem that uses one part of it, well, now there's these other use cases that you might be able to pull in for very small deltas. And it's kind of a set of standards that works across all of these different use cases instead of one standard that doesn't really fit anything quite that well. So very briefly, OAuth is not defined outside of HTTP, although the Kitten working group came up with a GSS API extension that allows you to do it over lots of non-HTTP protocols. The ACE working group is working on a way to do OAuth over CoAP. It is not OAuth. It is OSCOR. They renamed it. Do you guys remember? Okay. I'll have to bug Francesca about this, but there's a version of OAuth that runs over CoAP for CoAP and Core for sort of embedded devices kind of stuff. And to the previous point about what OAuth is, it is not an authentication protocol. It is very definitively not an authentication protocol. It relies on authentication, so the user has to authenticate so that that authorization server knows who everybody is and whatnot. The client authenticates, so there's authentication all through it. But authentication is all about communicating who the user is and why they're there and how sure are you of all of this kind of stuff. OAuth doesn't do any of that. It doesn't communicate any of that. It very explicitly stays out of that. However, OAuth gets used to build authentication protocols such as OpenID Connect, which is built on top of OAuth. And so people using OpenID Connect think they're just using OAuth, where in fact they're using OAuth plus a couple of key components that makes it into an authentication protocol. Excuse me. OAuth is about user to software delegation, not user to user delegation. If you want that, you need to add a few more components. There's one standard out there, user managed access or UMA, that allows you to do that. Again, built on top of OAuth. OAuth doesn't give you authorization processing. This really isn't like XAML. XACML. It's also not like SAML in that there's not a way to describe, oh, when you get this, here's how you process it, and here's these rules to apply and stuff like that. Now, OAuth is really just about carrying that handle from one end to the other, and what you do with that handle, OAuth doesn't care. What you do with that token in order to interpret it, OAuth really doesn't care. There are lots of standard methods defined in how you do that, but those really aren't OAuth. They're added on to OAuth. Like we said before, OAuth doesn't have a token format, but it needs to have a format that both the authorization server and protected resources can make sense of. Even if it's opaque to the client, it's not necessarily opaque to everybody in the system. So there are token formats. JSON Web Token, or JOT, is one of the most popular ones out there, and it's a useful common format. And OAuth doesn't define its own cryptographic methods. OAuth 1.0 did. There was this fairly complex custom signature algorithm that got applied across all of the different HTTP query parameters and stuff like that. OAuth 2 said, you know what, that's the part that people are getting wrong and ignoring most of the time. And it also made people believe that they didn't need TLS across their HTTP connections, which is, of course, idiotic. So in order to avoid all of that, OAuth 2 said, you know what, we're not getting into the signature game, at least in the base protocol. So use TLS for everything and go from there. And like we said before, it's not a single protocol. I'm not going to reiterate that. All right. Deep breath. We're halfway through. How's everybody doing? Good? All right. Everybody checking your email? Awesome. Now, I've been to these tutorials. I know how it works. And so we are now going to dive deep into the canonical flow of OAuth 2.0. This is the authorization code flow. These are all the pieces, and this is what it looks like. All right, everybody got that? Awesome. Before we get into the details of what that diagram looks like, you need to understand that OAuth makes use of two different kinds of communication. It is an HTTP-based protocol. So first off, we have the back channel. This is just straight up HTTP calls. You make an HTTP request, get an HTTP response. That means that we've got headers, we've got the body content, we've got different URI parameters and stuff like that, different HTTP verbs that we can use. Really, really rich messaging system, and it's directly between two components. So between the client and the auth server, the client and the protected resource. This is where we're going to stuff sort of like the really secret things that we care about, like those tokens that we were talking about before. This is where they like to live in the back channel, talking directly between components. The front channel, on the other hand, is what we do when we get a user involved. Because notice in this back channel, when the client is talking to the HTTP resource, to the authorization server over HTTP, the client is going to say like, oh, I'm here on behalf of this user, and the authorization server, well, how does it know that the user is even involved in that process? Used to be, we knew because the user gave their password to the client, or presumably gave their password to the client. Those were scare quotes to anybody only listening to the audio stream. And in that case, the client's really just impersonating the user. So in OAuth, what we do is we use the front channel. We use somebody sitting in a web browser to interact with the authorization server. But the thing is, we're no longer talking directly between components. So how can we send messages here? Well, a front channel request and response is actually a stack of HTTP requests and responses. What it means is that in order for the client to send a message to the authorization server through the front channel, it sends a redirect to the user's browser to a very specific URL. That URL is hosted at the authorization server, and it's got a bunch of query parameters on it that are set by the client. Now that redirect goes to the browser, and then the browser, not the client, makes the HTTP request back to the authorization server. That means we now have an HTTP channel between the resource owner and the authorization server. The client is not part of that, which means that the resource owner, they can now authenticate. We can do, all sorts of session mapping and heuristic evaluation of security and all of that other good stuff that we like to do on interactive HTTP sessions without involving the client directly. So none of that leaks to the client. That's all really great. It also means that now that we are between the browser and the authorization server, we can do multiple requests. We can redirect internally, we can go off to other sites and then come back and all this other stuff. Now, how does the authorization server get any messages from the client in this if they're coming from the browser? Well, that URL that the client redirected us to has a bunch of query parameters on it that have values on those query parameters that are then received and interpreted by the authorization server. So you're not just going to a fixed URL, you're going to a URL with a bunch of parameters that say, I am this client, this is the kind of stuff that I'm asking for. Then to get information back to the client, we do the same process, but only in reverse. The authorization server sends a redirect to the browser that says, go load this URL. What that redirect looks like varies depending on the kind of client. In the canonical case where we're talking about, we've got two websites that are talking to each other. Well, that's going to be just an HTTPS URL that has a bunch of query parameters on it that act as the response to that front channel request. All right. We do this in order to separate the information. We use the front channel when the user's involved and the back channel as much as possible wherever the user's not directly involved. The front channel is going through a third component. It's going through the browser. We can't always trust it to make sure that messages always get through exactly how we want to, because they can be sort of, snooped and modified. That is assumed in the OAuth protocol, and there are protections in the OAuth protocol to mitigate that type of stuff. But we use the back channel for all of the secret things as much as we can. So now we're going to go step by step through that crazy diagram. All right. First off, user shows up at the client and says, I want you to use that protected resource. And the client says, I can't do that. I need you to go get me permission before I can go do that. Right? Whereas in the past, the client would just say, great, give me your password and I promise I'll be nice. Now the client says, all right, go talk to this other server and they'll come up with something that I can use. So just go over there, do what they say, and come back. So we send an HTTP front channel response. We send a redirect to the browser, and then the user goes and talks to the auth server. Now, at this point, the user can authenticate to the auth server. Whereas previously we were stuck with credentials that had to be copyable, like passwords, we can now do multi-factor authentication. We can do, massive risk-based engines like most of the large internet providers do today. You can do pretty much whatever you want between the user and the auth server, and it's a very rich channel of communication because it's the web, right? So the user authenticates, so the auth server now knows who the user is. And the auth server knows who the client claims to be because of those query parameters that were in that redirect. So we can now say like, okay, so it looks like this client is asking to do these things. Is that okay with you? Now, back when we were just asking for somebody's password or just stealing their password on the way through, we didn't have any way to ask the user if this is what they are trying to do. We now have a place where we can ask the user, the resource owner, is this your intent? Are you actually trying to get this client to go talk to this resource server? Do you really want to log into Farmville with your Facebook account? Is that what you meant to do today? And it seems funny to give that kind of control to an end user, especially to a lot of security architects, but think about it in terms of who is in the best position to know what they're trying to do. It's the user. They know what they're trying to accomplish. They may not know what they're really doing, but they know what they're trying to accomplish. So this is an area of active research of how to best communicate this decision and gather this consent. And a lot of work that I do is kind of in this space. I could rant about that for several hours. I won't, but ping me after if you want that. Point here is that we can ask the user, did you mean to do this? Do you approve? If you do approve, you send back this thing called the authorization code. Now that authorization code is a temporary credential drawn here as a little paper carnival ticket that gets sent back to the client. How does it get sent back? Through a redirect through the front channel, just like we were talking about before. It's a query parameter that goes through the browser. The browser makes a request to the client, and that gets sent back there. So now the client has everything that it needs to go talk to the authorization server and get the real credential. That paper ticket really isn't good for accessing the protected resource. It's not meant for that. What it's meant for is the client to then turn around and then talk directly to the authorization server in the back channel. At this point, though, the client can now authenticate itself. It can now prove that, yes, I am the piece of software that was making that original request. And there are a few different ways to pull this off. That way, the authorization server can say, like, oh, yeah, this is who I told the user it was who was trying to access their stuff. You proved that you are, the same entity that made that request. We're good to go. I'm going to give you a token, an access token. That access token can then be used to call the protected resource by the client. And you notice that, once the user said everything was okay, they kind of got out of the process. Because remember, the ultimate goal is getting the client something so that it can do things on behalf of the user. The user's no longer on the HTTP transactions. They're no longer really directly involved. Once the user says, yes, this is okay, we're good with them. In a nutshell, that's how OAuth works. It's about delegating that access and going through this so that you get that token to the client so that it can call the protected resource. Now, there are a bunch of things that have been added to OAuth or sort of built into OAuth that allow this to work in less than idealized situations that we call the real world. And one of those is this concept called a refresh token. So far, we've been talking about a thing called an access token. Access tokens, once the user's said okay, they keep working. The user can log off of the client. They can wander away. They can get eaten by an alligator. Doesn't matter. OAuth doesn't care. What OAuth cares about is that that access token is still good. So the client's going to keep using that access token as long as it's good. And this is a key design point. OAuth is designed to work when the user isn't there. And it's also designed to deal with a situation like, well, when does that access token stop working? Maybe it expires. Maybe the user wasn't eaten by an alligator, but they logged into the authorization server and said, you know what, I don't like that app accessing my stuff anymore. I want to revoke access to that. So that access token is going to stop working. So what does the client do then? Well, if you did OAuth to get a token in the first place, you can just do OAuth again to get a token again. You always have that option. So the failure mode of OAuth is more OAuth, which is a deliberate design decision, because if you think about the array of different components in an OAuth ecosystem, you're probably going to have one authorization server, a handful of protected resources, and a whole bunch of clients whose main job is not to do security. Security is the thing that they have to do in order to call the API and do the stuff that they really want to do. So with OAuth 2, we made deliberate design decisions to allow the clients to be as dumb as possible. One of the best ways to do this is to not have complex if-then-else code paths for error handling. If you get into this place, like, you always assume that your token might not work. And if your token doesn't work, okay, maybe go try to get a new token, which is great if your user's still there. But if your user has in fact wandered off, you can't ask them right away and you can't call that API again. What do you do then? Well, there's a construct called a refresh token. And what that means is that the refresh token is something that you get alongside the access token. It's not good for calling APIs. It's not good for getting the data to the client. What it is good for is saying that I have proof that the user said that it was okay to use this API, but my access token isn't good anymore. So give me a new access token so that I can keep calling the API without bugging the user. This way, your access token can live for maybe a couple minutes. So it's just kind of sitting out on the wire for a few minutes. App goes to sleep, whatever. It's not calling the API anymore. Access token times out. App wakes up, a couple days later and says, I need to go refresh that API. Access token isn't good anymore, but I have a refresh token. I have a refresh token that allows me to go and get a new access token. And that refresh token basically says, hey, the user said this was okay. Unlike the access token, which is a bearer credential, at least in its most basic format, refresh token is not. Refresh token has to be presented alongside the client's credentials, just like that authorization code we saw before, and it's only presented in the back channel. It only ever lives between the client and the authorization server. So protected resources never see this. All right? Refresh token's a really simple concept, but it's really, really powerful because it allows you to really dial in the risk between all of these different credentials getting stolen. All right. Another concept that's built into OAuth is when I'm calling this API, maybe I don't want my API to be all or nothing. So back in the day when it was just username and password, if I had the username and password, I could do anything I wanted to on the API because it was the whole API. It was on or off. But now that I've got this delegated token, I can probably do a better job at splitting that up. So we use the concept in OAuth of a scope of that token. Now, the scope of the token is used to represent a lot of different concepts. Most commonly, it's the type of thing you're allowed to do. Am I allowed to read this API? Am I allowed to write to this API? What kinds of things? Also, you often see the kind of thing that you're allowed to make actions on. So, am I allowed to get your timeline, your profile information, the metadata of your attributes versus the attribute values themselves? What am I allowed to do? And occasionally, it also means when you can do this. Can I do this when the user's not logged into that main service anymore? Can I do this only when they're online? Can I do this only on Tuesdays at 2 p.m.? Right? What are my different options? Oh, Meet Echo, I think our camera fell asleep, just FYI. So I think MeetEcho fell over, but we're going to keep going here in the room until they do that. If anybody's in the chat room, can somebody at MeetEcho? So OAuth scopes are strings. They're just very simple strings that don't have spaces in them. That's really their base definition. OAuth doesn't say which parts of this you're allowed to use a scope for. It just says it's a thing that says what the token's good for, and it just gets out of the way. Which is a good thing because it allows you to design your API in sort of very specific ways. And it's a bad thing because everybody uses scopes in slightly different incompatible ways, which can be really frustrating to developers who, of course, don't have to call just one API in their day-to-day lives. Now, the resource owner approves the scopes, and those get bound into the access token. So when the access token shows up with the protected resource, it can figure out these are the scopes that it's allowed for, and it can make that decision of how to interpret the incoming response. Yeah, I think MeetEcho is still down. All right. All right. So far, we have looked at the authorization code flow and kind of the basics of how OAuth works. Fundamentally, it's a delegation protocol. It's all about a user saying this software can do it. In the world that OAuth was originally designed for, I think we're waking up. Yay! Thank you, MeetEcho. And in the world that OAuth was originally designed for, it was all about a web server talking to another web server. All right? That's not the world we live in anymore. We've got in-browser applications. We've got native applications. We've got apps that never see a user, things that are just poking around data centers talking to each other. It would be really nice to use this security layer that we've invented across all of those things. And in fact, that's what happened with OAuth 1, which was never intended to solve all of those cases. But it was kind of used for that anyway, because it almost solved people's problems and they just kind of hammered it into, the square peg into the round hole to make it fit. With OAuth 2, instead of giving everybody a square peg, we gave you a way to make your own custom-shaped pegs with a couple of patterns that are fairly common. Yeah, I'm way stretching this metaphor. So this canonical use is all about server talking to another server, a web server talking to a web API. Those types of systems have particular aspects. For example, a web server can keep secrets from the users. That's not true with an in-browser application, because anything that's running in your browser, you can inspect it. You can't do that with a remote web server unless they have other problems. For a native application, similar thing. It's running on your device. Developers can think that they've got it all nice and locked down. Most of the time, you can inspect and do some fun things with that as well. And there's all these different kinds of delegation that we could do, right? So we're going to look at a few different ways that you can use OAuth 2 beyond the authorization code flow. I will say, though, that if you're just learning OAuth 2, start with the authorization code flow for two reasons. One, it really is the most robust and the most widely used version of OAuth 2. It solves the widest set of different use cases. And two, and it really should be your default based on that. And two, everything else that I'm about to talk about here is an optimization of the authorization code flow for different specific purposes. And every time you have an optimization, you have to make assumptions about what you're optimizing for. All right? It means you're making assumptions about the environment that you're in. You're making assumptions about the clients and the users and the APIs. Everything that I'm going to talk about in the next few slides here is going to really be for specific environments and circumstances. And one of the ones that gets misused the most, and so I'm starting with it, is the implicit flow. The implicit flow is what happens when you shove the client up inside the browser. Now, the authorization code flow goes through a lot of different steps to make sure that things like the client's credentials and the client's identity and authorization never leaks to the end user, that the access tokens aren't exposed to the browser and all of this other stuff. But what if your application is running literally inside your browser? It's a JavaScript application that is executing inside the browser at runtime. All of that stuff that you've done, all of those hoops that you've just jumped through to make sure all of that stuff is secret from the browser really doesn't apply anymore. Because it's all in the browser. It's all in there. And so the implicit flow, in order to get the access token, is really a front channel only flow. So what you can do is you send the user over, and instead of coming back with an authorization code that you then go and repost and then get the token, you send the user over and they come back directly with an access token. And herein lies the trouble. Because that's great for an in-browser web application, because now you're bound by same origin policies, and it comes back as the HTTP URL fragment. So it doesn't, depending on your browser, thank you Google, it usually doesn't get sent across redirects or posted back to servers or things like that. So it's supposed to stay nice and inside the browser. Doesn't always these days, which is fun. But if you're using this, the implicit flow, in any other kind of application, you're breaking all of the assumptions that went into it. So this is the biggest problem I have with the implicit flow. Not its design in and of itself, because for an in-browser app, it works pretty well. We didn't have HTTP post message when this came out. These days, we'd probably use that instead, right? But a lot of people see this and they say, you know what? This is simpler. This is easier. And I don't know why I'm doing all these redirects and HTTP calls and this auth code and all this other stuff like that. I'm just going to do the implicit flow until something breaks, and then I'll go figure out what this OAuth thing is. I see this time and time again, and this mistake has been at the core of a number of very large-scale attacks, including one that did a lot of damage to ESPN.com. Again, more details on that after the talk if anybody wants to ping me about it. The problem is that the simplicity of the implicit flow comes at the cost of assuming that everything is going to stay right inside this little box. Those assumptions go completely out the door when you're using a native application, when you're using a web server-based application, or really anything else other than something living directly and completely inside the browser. And in order to encourage people to use this correctly, when we wrote OAuth 2, we made sure that you can't get a refresh token here. Well, why not? Because, well, if the user's there in the browser, you can just send them back and go get a new access token because they're still there. But a lot of people will start using the implicit flow in other types of client apps and say, well, okay, my user went away and now I need a refresh token. How do I get that? So even though we tried to design that into the protocol, it didn't quite sink in. So I really can't recommend the implicit flow unless you are very much in this very tight constraint, right? Now, the client credentials flow is another fun one, because you take the four parties of the authorization code flow, except that you kind of take the resource owner and conceptually squish them down into the client. The whole idea for this is that, well, I'm really kind of solving the API key use case. Now, at the beginning of the talk, we talked about how people use API keys to say, like, I am here on behalf of this one specific user. Well, that's not the only way we use API keys. Sometimes we say API keys are, hi, I am this client. I'm not here on behalf of a user. I'm here on behalf of me. And so API, let me in and let me do my client things here. Previously, those API keys would have to be known by all of the protected resources, who would then need to go and validate that, yes, this is this specific client talking to me and they're allowed to do this. And managing all of that was really kind of complex. The client credentials flow in OAuth simplifies that, because now the client takes its credential that represents itself and it goes and talks to the authorization server and gets back a plain old access token. Then it uses that access token to call the protected resource. Now that client is not going to get, again, it's not going to get a refresh token because it can just go get a new token anytime it needs to because it has its own credentials. It's not on behalf of a user, so there's no user to bother. And that access token can then be used for all of these different protected resources. But the protected resource never needs to know the client's credentials, right? I've only got like 5 minutes left, so I'm going to burn through this. Next up, one of my personal favorites, the resource owner password flow. This is all about stealing the password. This is the client saying, give me your password and I'll go call an API and I promise I'll be nice. Now, hold on a sec. We said that this was really bad. And it is. So don't use this one. But I'm still going to tell you how to do it so you know not to use it, if that makes sense, which is why we specified it. Basically, when you get the user's password, instead of calling all of the APIs, you call the authorization server and get an access token and then call the protected resources. Now your protected resources don't need to know the user's password. They just need to be able to understand OAuth access tokens. This is really was intended at the time for legacy applications, which would then move to the authorization code flow, except that what happened is we put it in the standard and everybody said, hey, that's easy, and went and just used that instead forever, which was never our intent. Thank you. So that's a really bad thing. The assertion flows, if you're talking to Microsoft, you care about this, otherwise, meh. The device flow is all about a limited access client. We're seeing a lot more of these days. So this is not in the core OAuth specifications. This is in an extension that's working its way through the working group right now. The whole idea here is that your device starts an OAuth process, and then it gives you a random code from the authorization server that you then go and plug in using another device. If you've ever used a set-top box to like connect to Yahoo or something like that, this is what you're doing. You're actually participating in an OAuth dance with multiple devices. So what happens is you type in that code to the authorization server, or you scan a generated barcode or anything like that. The authorization server says, hey, I've got a request that was waiting for this. I'm now going to bind it to your account, and I'm going to send you across and give you an access token. At the end of all of those, you get an access token, and all of your protected resources speak those. Now, native clients, very quickly, are things that are running on your devices, stuff that's running on your phone, on your laptop, stuff like that. They functionally live outside the browser, so this is a different world. So instead of accessing the content through your system browser, you're working directly with an application, right? That means really two things. One, you got to deal with secrets, and two, you got to be able to get information back in the front channel. Now, dealing with secrets is really kind of a problem because a native application isn't very good at keeping a secret from the user, because the user can always poke in. Anybody in this room could go and poke in and figure out what secrets are there, which means that if you have the same application installed on 1,000 different devices and you've got the same secret, it's not really a secret anymore. OAuth 1 assumed that it always would be, which was a mistake. In OAuth 2, we said, you know what? Don't pretend anymore that that's a secret. So you can either use dynamic client registration to give every instance a new secret, which is an extension to OAuth, or you can use a public client, which doesn't have a secret. Now, how do we protect those? Oops, I put these in a weird order. Sorry, when I trim down the slides, it's a lot of my transitions are what got cut. Now, to deal with that secret instead, we can use this thing called Pixie. Now, Pixie, I remember why I did this in this order. Right. So, thoughts on Pixies in a moment. How do you get information back to the client in the first place? Well, you need a redirect URI. If you're running a web server, that's awesome. It's just HTTP. If you're running a native application, you've got a few different options. You can do a custom URI scheme, which is far and away the most common these days. You can have some sort of locally hosted random web server. Google's starting to do this more on their apps. And you can have a remote host with either push notification or remote URL capture on the native device. I'm not going to go into detail how these work. They're all platform specific. The TLDR version is that there are ways to get information back to a non-HTTP server using OAuth today. Now, the problem with those custom schemes is that on today's platforms, anybody can register for any scheme. It's just you pop up, you say, hi, I'm an app, I want this one. And system says, okay. So combine those two aspects, the fact that anybody can get any scheme and the client no longer has a secret to authenticate the instance, you come up with the world where Pixie starts to make sense. Now, Pixie, proof key for code exchange. Very shortly, the client generates a secret, hashes it, sends the hash to the authorization server in the front channel. Authorization server does its normal dance, sends you back the authorization code. Then when you send back the authorization code, you send the non-hashed secret alongside of it to prove that you were the one that made that initial request. This allows you to tie into that transaction without having a unique identity for the client. In other words, you don't need the client credentials to get a similar level, not quite the same, but a similar level of security here. You can verify the challenge here because you now have the native, you've saved the hash from before, you regenerate the hash, and you're good to go. All right. There are lots of different use cases for all of these different grant types. This is really how you should go about choosing them. The first question that you ask is not, do I have a native application? Am I running in a browser? It's who am I delegating for? OAuth is fundamentally a delegation protocol. The first question you should be asking is, who am I delegating for? Is it an end user? Is it some third-party entity that's issuing assertions? Or is it just me? Once you know who you're delegating for, then you can start to determine which kind of clients that you're going to be using, and therefore which flows you're going to be using. OpenID Connect is identity on top of this. We don't have time to get into it. Dynamic registration lets you get clients, blah, blah, blah. Token introspection. We don't have time for all this. There's a lot of stuff with OAuth. This is why token binding is a bad idea. More on that on Wednesday. All right. Wrapping up. There is a survey. If anybody wants, you can write that down. Say how good this tutorial was or how terrible it was. Let ISOC know either way. And that link should be getting passed around as well. And that's it. Unfortunately, we're out of time. I can't go into detail on the other stuff. Like I said, there was a lot of content here to cover. Thank you all for your attention, and I will see you around this week. Thank you. And once again, anybody that wants the discount code for the OAuth in Action book, come talk to me. Thanks. Yeah, it's hard because sometimes things go a little long or a little short in different parts. So
just no comment. I might have.
okay. Hello.
What's next?
Oh, okay.
Oh,
Sorry, are you starting at 1:30 or
45.
Okay, good.
A 15-minute break in between.
That's good. I was hoping that they had done something like that.
Oh yeah. Oh yeah.
All right, so here's the clicker. This is set up for HDMI output, but VGA behind it, so whatever you can do there.
Okay, so that's present off of this.
No, this is my laptop.
Oh, that's your laptop. Okay.
So this is going away.
Okay, so this is a clicker, and that's got the there
It's
it
got
is.
the USB stick
Thank you.
right on
Good.
it. Yep,
Good.
already got that set up.
Off of my laptop.
Exactly.
Okay, thank you.
And that will automatically tie everything into Meet Echo. So, because this goes into their splitter, so that's why you have to use this one.
Shouldn't be a problem. I do need a little piece of magic to make that work. I think I have the electronic horseshoe now.
Fantastic. If not, the Secretariat, it should be floating around, and they've got a million adapters. So,
All right.
All
Enjoy.
right, you too. Good luck. Hi.
Ready. Oh, it's back here. Ready? Yeah, we can make that work. Just a minute here. That work is okay.
And by the way, this is how you recognize
Well, if you're really, really lucky, that's an HDMI port. Yes, it is. All right. Cool. Okay, let's go.
So ultimately, whoever is
Make this work. All right, so zip that up. All right.
And so, exactly. So that is the case of the service provider model.
All right.
Either use cloud system, built system on cloud, and then you know something, where you cover your eyes and say no, and people find ways to do it first. I don't think you can do it at the same time without the service technology. And so you're going to take
Okay. No, leave me alone. Okay. All right, now step one is put that there. That was interesting.